So in section 4 we can finally start with control, and what we'll do is state feedback control. So we're given a linear state space description of a plant, and we'll call it the open loop state equation, right? So we have here a system with P outputs, so this one lives in RP. It has M inputs, so this one lives in Rm, and the state as n. Well, the state is a vector of n components, so this one lives in Rn. So we would like to modify this open loop behavior to a closed loop behavior that we would like to master and impose. And for that we are going to use a control law, and the control law that we're going to use is as follows. So U, the input, is n times R. R is the reference signal or the set point signal. Okay, so this is the first term. It comes from the set point, from the reference, and therefore n is called the feed forward gain. There is here a second term that comes from the state, and this is really feedback from the state. This is why we call this state feedback, and the K matrix is therefore called the feedback gain. Note that this is a static law, right? That is really easy to implement because it only involves addition and multiplication. You can see here, as we said before, that this one lives in Rm, this one lives in Rn, and since we have M control inputs, we'll use also M set point signal. So this one will also live in Rm, which means that N lives in Rm times M. It has M rows, M columns, and K lives in Rm times N. In the case when there is one input, then K becomes K, and then we have something that lives in R1 times N. Okay, so K here is a row vector in this case, but this is only in the case where you have only one input. So remember that the open loop state equation was x dot is equal to ax plus bu, and that we use a control of the type nr minus kx, right? If you inject this one over here in here, this is what you will obtain. The output equation will not change. Okay, so we'll have x dot is equal to ax plus bnr minus b times kx, right? So the terms in x over here, we can group them. Okay, so remember that b is in Rn times m, and k was in Rm times n. So obviously bk is in Rn times n. So this is possible. The two matrices have the same dimensions. Okay, so the closed loop state equation is a minus bk, and the closed loop control equation is now b times n. Well, the output equation has not changed, so the output matrix remains unchanged. Here you see things graphically, so you see that x dot is bu plus ax, right? So this is implementing this thing over here, right? And you see here that u is indeed r that goes into n minus kx. So this is indeed the feed forward part, and this thing here, because it comes back from the state, is the state feedback part. So remember that we are using a command which is nr minus kx, right? And that the closed loop state equation is a minus bk. So the idea here is to, well, choose a feedback gain matrix k such that this matrix, okay, the state matrix of the closed loop system is asymptotically stable, which means that the real parts of the eigenvalues are negative, right? Well, stability has to do with this feedback part. We'll see later on that this feed forward part can be used to make sure that you have a zero state error. This type of law, as I said before, is a static law. The output here, u of t, the output of the control law, of course, output of the control law at time t only depends on the reference and the state at the same time. So assumed here is that all the states x are available for measurement. We will see in the next section what you can do if this is not the case, okay? Because very often some states cannot be measured because there is no sensor, okay? There is no technology, for instance, to measure that variable, or there is a sensor but the cost is too high, okay? So in very often not all the states will be available for measurement, and what we'll do, and this is the main topic of the next section, is to construct an observer, or another word for that is a state estimator. And what it will do, it will reconstruct the state that is not measured from the inputs and from the outputs that are the y's that are measured. Well, in this slide what we do is compute the feed forward gain n, but we suppose that the feedback gain k is already available, and we'll see later in the course how we can obtain it. So what we'll do is obtain the closed loop transfer matrix, and we have just seen that the realization in closed loop is a minus bk, right? Then bn, this is the new, well, b, and c, right? And if we construct the transfer matrix, and this is something that we have been doing before, well, we take c and then si minus this one, and whole thing inverse bn. And if you reshuffle the signs, this is what you obtain. For a single input, single output system, the static gain is simply the relation between the input and output in steady state, and it can be obtained from the transfer function by taking this transfer function and replacing s by 0. In the multivariable case, the static gain matrix now links the steady state input, and in this case it is a reference or set point signal, to the steady state output, right? And in the multivariable case, what you have to do is, well, take the transfer matrix that we have over here and evaluate it in S is equal to 0. So here we have the static gain matrix, right? And since we want the output to follow the reference, this one should be the identity matrix, right? So what we can now do is compute this, right, by simply replacing S by 0, and this is here the static gain matrix. And if we equate this one to an identity matrix, right, this is the relation that you obtain, and N can be computed as follows. In the single input, single output case, well, this will simplify to something that is much simpler, right? Because we have only one reference signal and one output signal that is being controlled. So the feed-forward gain becomes simply a scalar. Well, let us have a look at this one again, more in particular in the case of a unit step response, right? So what we'll do is consider the reference input, and this one is a vector in Rm, right? M is the number of actuators. The number of outputs that you can control is the number of actuators that you have at your disposal, right? So R, the reference signal, is in Rm, and we consider unit steps. So you'll have a vector with a number of unit steps, so you'll find 1 over S a number of times. Now we are interested in the steady state response that we've written like this, and it's also therefore a vector in Rm. These are the M outputs that are controlled using the M actuators. By definition, it is the limit when t tends to infinity of y of t, and we can now use the final value theorem. So we have limit when s tends to 0 of s y of s, right? But y of s, it's the closed loop transfer matrix times the reference vector, right? So we can write it as limit when s tends to 0 of s closed loop transfer matrix, right? And this one we'll rewrite it slightly differently. We'll put the 1 over s in front, and therefore we have here a vector with a number of ones, exactly m ones, right? So this one and this one cancel out, and this results in h closed loop evaluated in s is equal to 0 times this vector composed of ones, right? And this is what we mean by the steady state set point. Indeed, if you have a unit step, right, when t tends to infinity, the value of the reference tends to 1, right? And what do you expect at the output? Well, a vector composed here of ones, right? We want the output to follow the reference. So therefore this one must be the identity matrix. We've just seen how you can compute the feed-forward gain n in order to produce a zero steady state error. That is that the steady state response follows the reference signal. As you can see, this is only in the absence of modeling errors. So this means that this way of producing the zero steady state error is not robust, because n computed to produce this zero steady state error is based on a model of the process, and this model has a realization A, B and C. And of course a model is always an approximation of the actual system. So if you use this n on the actual system, there will be a slight steady state error, right? Think of a system that is non-linear. You'll design your controller based on a linearization that is only valid in the proximity of the working point. As soon as you go away from this working point, your model is not correct anymore, right? And it could therefore be that your feedforward gain n is not exact to produce a zero steady state error. We'll see later in the course that you can produce a zero steady state error by introducing integral action in the state space design. We will see in this course and also during the control lab that the matrix C is really dependent on the simulation. So suppose that you have a state that is x1, x2, x3 and x4, right? And that, for instance, only state x2 and x4 are available for measurement, and that you have a single input, single output system, and that only state x4 is controlled. Well, really there are three situations for the C. If you implement your model, for instance, in MATLAB Simulink, and you want to have a look at all the states, what you will simply do is y is equal to cx, and since you want to have a look at all the states, you'll say that C here is the identity matrix of dimension 4. So that's a first case of a typical C. In this case here of control, right, the x, the state that is being controlled is x4. So in these equations here, to compute the n, you will have to use a C that will isolate the fourth state. Okay, so for control in this case over here, you will use this C for control. Later on in the course, we'll construct an observer, and this observer will work with the states that are measured, right? Here x2 and x4 are measured, and the goal will be to obtain either an estimation of the full state or an estimation of the reduced state. Okay, x1, x3, these are the states that are not measured. But in any case, when we'll construct the observer, we'll have a C, and we'll call it C observer, that will isolate the states that are measured. And in this case, well, we'll isolate the first one, but the second one, and the fourth one. Okay, so you see that depending on the situation, the matrix C is very different. Well, to illustrate the concepts, I will use the three tank system. These are three tanks that are interconnected through pipes over here, and there is also an output discharge. This system has two inputs. It's the input flow into tank 1 and the input flow into tank 2. There are 3 states, H1, H2 and H3, and we will assume that only the level in tank 1 in tank 3 is measured, so we have H1 and H3 available for measurements. Okay, so since we have here 2 inputs, we'll have M is equal to 2 and N is equal to 3. The number of outputs is 2, so we'll have P is equal to 2, right? So now follows that A as dimension 3 times 3 and that B as dimension 3 times U. As I mentioned before, if you implement, well, a linearized version of this 3-tank system in MATLAB Simulink, you will probably need to have a look at all the 3 states, and then you'll use a C matrix, which is simply the identity matrix of dimension 3. This will allow you to have a look at the 3 states. Since here we have only access to the first level and the level of tank 3, well, if we want to implement a state feedback controller, we'll have to estimate H2. And we'll see in the next section that the C that you'll have to use for the observer will actually select the measurements that you have at your disposal. Here we'll assume that the state is H1, H2, H3. So if you want to select H1 and H3, well, the C that you should use for your observer design is the following one. 1, 0, 0, this will select X1, and 0, 0, 1 will select X3. Okay, now we're in a section on control. So we have 2 inputs, so we can have a reference signal, a set point signal with 2 set points. It's impossible to control the 3 heights independently of one another since we have only 2 inputs. So we'll assume here that the reference, okay, or the set point if you prefer, is equal to H1 set point and H2 set point, so that we are able to set the set points for the level in the first tank and in the second tank as a user. Well, in this case, this means that the C that we'll use for control will actually select the outputs that are being controlled, and this is, well, the level of tank 1 and the level of tank 2, so the 2 first states H1 and H2. So the C in this case will be 1, 0, 0. This will select the height 1, and 0, 1, 0, and this will select the second level. So you can see here again that these 3 C's, depending on the situation, are very different. So we can now have a look at the N, and the N is minus C A minus B K inverse B, the whole thing inverse. Okay, so in this case you can see that this matrix here is a 2 by 3 matrix. So we have here a 2 by 3 matrix. This matrix here is 3 by 3, and as you can see, B is 3 by 2. So you can see here that N will be a square matrix of dimension 2 by 2. We've said previously that before you do your state feedback design, you should always check if your pair AB is controllable, right? And this can be done by checking if the controllability matrix has full row rank. But if this is the case, well, you can assign the eigenvalues of a minus bk to any region of the complex plane by a suitable choice of k. Remember that the eigenvalues of a minus bk are the eigenvalues of the state matrix in closed loop. So these eigenvalues are actually the poles in closed loop. And of course, we'll assign them to the left half plane so that we have stability in closed loop. Okay, so we can show that all those statements are equivalent and that after state feedback the closed loop is still controllable. Well, what happens if the pair AB is not controllable? We have seen before that you can find a similarity transformation that will transform your state in a state X bar, where you have the following decomposition. This state is controllable and this state is not. Remember that this state is not controllable because of the presence of the zero over here. It cannot be influenced by the input and because of the influence of the zero over here, which means that it cannot be influenced indirectly through this part of the state. Okay, so if we now use a state feedback u is equal to minus k x bar, okay, so what we can do, as we have two parts of the state, a controllable part and an uncontrollable part, we can kind of divide our k similarly, right, and call it kc and kc bar. And if we inject this over here, right, and we do the calculations, what we'll see is what we have over here. So we can see here that the poles that are associated to the controllable parts, okay, they can be modified through this part here of the feedback matrix, but the uncontrollable part has still the same dynamics than in open loop. Okay, so the eigenvalues of the matrix over here that is related to the uncontrollable part cannot be changed. Okay, so if your system is not controllable, you better make sure that the part that is not controllable is at least stable, because otherwise you will have problems. But even if it is stable, it means that you cannot accelerate the dynamics of the uncontrollable parts. Okay, you will be able to change this dynamics here by a suitable choice of this matrix over here, but you'll have to live with the dynamics of the uncontrollable part. So here we look at the differences between cases where you have more than one input and cases where you have only one input. So suppose that m here is larger than 1. Remember that k lives in r m times n. Okay, so in this case there will be m times n entries in k, right? But we only have to place n eigenvalues. Okay, so you have only n constraints, but you have m times n parameters in k. So it means that we have m times more degrees of freedom than necessary. Okay, so this means that these degrees of freedom can be used for something else, and one way of using these degrees of freedom are to select k using optimal design. Okay, so we'll compute k when optimizing a cost function, and we'll see how this works later on. If m is equal to 1, okay, so for instance, if we have a single input, single output system, then the system reduces to this format. Okay, there is only one input, so the control law will have only one output, right? And k reduces to something that has dimensions r, that lives in r times n, so it's a row vector. Okay, so there are n elements in k, and there are n eigenvalues for a minus bk. Okay, so this means in this case that there are no degrees of freedom. So in the following we will see how we can do pole placement for single input, single output systems. Of course you can do pole placement also for multivariable systems, but we'll explain it only in the case of a single input, single output system. So we'll assume here that the system is in controller canonical form, and this is a form that we've seen previously. And if you're given a realization A, B, C, and we'll assume that the D is here 0 here, you can compute H of S, right? Bs over As. This is the characteristic polynomial, and it takes the form Sn plus a1 Sn minus 1 up to an. Okay, so you can construct this controller canonical form from the open loop characteristic polynomial. So suppose now that we are given a feedback, and remember that for a single input, single output system, K, the matrix K, reduces to a row vector with n elements. And then you know that if you use this feedback, well, in closed loop you'll have a state matrix A minus bk, right? But because of the particular structure of B in the controller canonical form, we have zeros everywhere except 1 at the end. Well, this matrix A minus bk becomes this matrix over here, and as you can see, only the last row is changed. But from what we have seen here previously, you can let's call this one POLP of S. It's the characteristic polynomial in open loop. Well, you can also obtain the characteristic polynomial in closed loop, and that will be s to the power n plus a1 plus k1 s to the power n minus 1, and so on up to an plus kn. Well, we've seen that if the system is in controller canonical form and you apply state feedback, you end up with a state matrix that is again in controller canonical form. The closed loop characteristic polynomial is given over here. So the idea here to design the state feedback is to choose desired pole locations for this closed loop polynomial. Okay, of course we'll put these poles to the left of the imaginary axis, but we'll see later on in more details how you can choose appropriate pole locations. But anyway, once we have chosen the appropriate pole locations, you have also constructed a desired closed loop polynomial, because the closed loop polynomial will be s minus p1 S minus P2 up to S minus Pn. Okay, so this is the desired closed loop polynomial, and as I've said, you choose it indirectly by choosing the pole locations. Here the pole locations can be real, but they can also be complex conjugate. Okay, so this is now the desired closed loop polynomial, and now the question is how you choose k, right? Well, this is what you desire, and you know that the closed loop characteristics polynomial is given over here, so we have to equate this equation with this equation. Okay, and you can do this for every parameter. So for instance, let's do it for the independent parameter here. Alpha n comes from the pole location, right? An comes from the system, it's a system property. It comes from the open loop characteristic polynomial, and now you can write that kn is alpha n minus an. This is kn over here. So this is how you can obtain the state feedback. So here's the pole placement algorithm that is implemented in MATLAB's command place. Okay, so the first thing that you have to do is you have to compute the open loop characteristic polynomial, because you'll probably start from a realization A, B, C that is not in the controller canonical form. So how can you obtain this open loop characteristic polynomial? Well, you compute the transfer function, okay, B of S over A of S, and here you find the characteristic, and this is what I've called here the open loop characteristic polynomial, and this is easy to do, right? And you should know it by now. It's S times the identity matrix minus A, the whole thing inverse times B, right? So you can obtain the open loop characteristic polynomial, and you have access to all the coefficients A1 to AN. So it's now time to bring this realization ABC to the controller canonical form. Here it says only AB because for the pole placement you don't really need the C over here. And we have seen that you can bring the system to the controller canonical form using a similarity transformation that is given over here. Okay, well, this similarity transformation is constructed from the controllability matrix of the original system. That's easy to obtain, right? It's B, AB, etc. up to A to the power n minus 1 B. And this controllability matrix can be constructed from the coefficients of the open loop characteristic polynomials, the parameters A1 to AN, right? So now we have our system in controller canonical form. Next thing that you have to do is to design the closed loop characteristic polynomial, and this polynomial you can obtain by choosing pole locations appropriately, and as I've said, we'll see how you can do this later. But choosing the pole locations gives you the closed loop characteristic polynomial. Okay, so what you can now do is construct the state feedback KC here that is valid for this controller canonical form, as we have shown in the previous slide. But this state feedback is valid for the system in controller canonical form, not for the system in the original realization. So what we'll have to do is compute the state feedback gain, right? k for the original system, and this is simply obtained by taking kc and multiplying by the inverse of the similarity transformation that we have used to bring the realization AB, the original realization, into the controller canonical form. As I've said, this method is implemented in MATLAB's command place. Here we have explained it in the single input and single output case, but it also works, of course, for MIMO systems. And if you remember, in the MIMO case, there are extra degrees of freedom, and MATLAB uses these extra degrees of freedom to find a solution that minimizes the sensitivity of the closed loop poles to perturbations in A and or B. So we have implemented a state feedback of the type that is shown here, and remember that we are working with single input, single output systems. And well, if you start from a controller canonical form and you apply this state feedback, you'll end up with a realization of the system in closed loop that is also in controller canonical form. Remember that the elements that you have got here on the last row of the state matrix here in closed loop are the ones that you find in the characteristic polynomial here at the denominator, and the ones that you find over here in the C row matrix are the ones that you find in the numerator. Okay, but these have not changed. Okay, so you see here that the only difference in the associated closed loop transfer function comes, of course, in the denominator and this scalar that you've got here. But you see here that the zeros of the transfer function are still exactly the same. So as a conclusion, state feedback can, of course, assign the system poles everywhere you want. Of course, you'll put them to the left of the imaginary axis, but it has no effect on system zeros. Well, you can see, for instance, that in pendulum or inverse pendulum type systems, there is a zero in the transfer function to the right of the imaginary axis, and this zero that is placed to the right of the imaginary axis causes a so-called inverse response. Since using state feedback you cannot affect the system zeros, well, this zero will remain at the same place in the closed loop transfer function. So in closed loop you will also see the effect of this zero to the right of the imaginary axis, and you will still have this inverse type response. In the teaching unit, digital control, we will see that there is a design method called the RST method that allows you to also affect the system zeros. This RST method applies a so-called 2-degree of freedom controller. Well, there is also a method based on Ackermann's formula that allows you to do pole placement, and well, I will not mention this in this course and I will not go into the details of it, but you should not use the underlying MATLAB command Ackermann, okay, which can also be used to do pole placement, because it only works for scissor systems, and this method is not numerically reliable when the number of states grows.